One, one. Can you hear me now? Hello? Okay, thank you. Great. All right. Focus. Any questions from the Zoom world? Do you guys have any questions? Hello. All right. I have to wait. No, I can start. Good. All right. Okay, I'll wait. Yes. Any questions from the audience? The physical and the metaphysical? Nothing? All right. Yeah, let's go. All right. So yeah, the matrix was not symmetric. So let me do this example from scratch. So here's the quadratic, and we want to minimize with boundary constraints. Okay, this is called box constraints. It's the hypercube. And this is the symmetric matrix. All right. And we talked about last time about computing this gradient, right? If you can avoid partial derivatives, even today, do it. Try to use our results. If you want to take partial. It's up to you. Whatever is fastest. I don't know exactly what's fastest. Okay. Yes, so we did this last time, and this is a trick because we know that directional derivative satisfies the formula dvf is equal to v gradient of f. So this is easy to compute. This can be annoying to get closed form. Right? So the advice is if you want to get closed form, start from the left, just do the limit, and then extract your gradient from the formula. Okay, do you understand? Is that okay? All right, good. So from this formula, you can read off the gradient of the function. No partials. So we're back to first year calculus. All right. So matrix is symmetric, and you're just left with this 113x plus 1, and we want to find stationary points. Can someone tell me when is this guy? What's the minimizer? Not like the point, just like what should I put on the right? How will I? What do you think? What? What do I put here? Not the vector. You don't have to compute the vector. Just how would you compute it? I'm not moving till someone tells me. Sorry. Yeah. So what do I do? Yeah. Thank you very much. That wasn't hard, was it? Good. All right. So then we will use our theorem to compute this stuff. So our theorem says that, let me go back to our theorem very quickly. So where is it? Yeah, this is our theorem. So this theorem says if you are in a box constraint and your guy is convex, which I would show it to you that it is convex. You have if and only if. So this if and only if x star is local min, and if you are at the lower bound, your partial is positive. If you're at the upper bound of the box, BI, you're negative, and internally you're 0. Okay, so we talked about this last time with student, human, that this goes back and forth, but you need all 3 conditions. So I had to add one more. Okay, is that okay? All right. Good. And I mean, you need convexity here. I'm talking about convex case. You understand? Right? We replaced then by if. Is that okay? What you mean? You're looking, tell me. On the left, okay, sorry. I mean, X star is local min. We talked about this last time. No, like if you want to go both directions. If you want to go like to the left, right? Remember? Okay, I don't know. I mean, we can talk about it. All right. Okay, blah, blah, blah. So first of all, why is our guy convex, GX? Like, why is this guy over here convex? Because why? What is a double? Huh? Yeah, the Hessian will be what? Which matrix is it? It's just A, right? Yeah, which is a positive definite. Is that okay? Do you understand? Okay, you can let me know. I mean, I don't know, like if it's obvious, like, is it okay? Okay, okay. I'm not sure. All right, so box constraints. Lower bound tells you partial has to increase in order for you to stay inside. Okay, so the picture you should have in mind. Yes, question. Sure. No? Okay, never mind. If you're in the lower bound, your partial needs to increase. So if x star is in the lower bound of the cube, in order to have a local min there, you will need to be increasing. Okay, and yeah, let's do that first. All right, so you plug in your stuff. This is your function, and in coordinates if you like it. So let's go to our guy. So let me explain how you get this. So we had 1, 1, 1, 3, x1, x2 plus 1, 1. And you take, so which coordinate do I take? There's two coordinates. What do you think? What should I put here? Huh? 1, right? Yeah, perfect. So yeah, so you have x1 plus x2, x1 plus 3x2 plus 1 and 1. And you take the first component, which is x1 plus x2 plus 1. Is that okay? Do you guys understand? Is that okay? Okay, good. So you're asking for this guy to be non-negative. This is the partial g, partial x1. Okay? And I can write it here as well, however you like it. So partial 1g, partial 2g. Okay? Is that okay? All right, good. And this is always possible, all right? So there's no contradiction, and it could be possible that your minimizer is at the lower bound, all right? I mean, I will give you the minimizer in a second, but yeah, anyway, so, but this is possible because xi's are in 0, 1. So you don't get any contradictions. All right, next one. Yeah, I will leave that to you, x2. So now if xi is equal to 1, then you're asking for the partial to be negative. Why is that? Because now you're at the upper bound. Okay. And now in order for this to be a local min and for you to stay in, you need to be going like this. So is that okay? Someone is, I don't know, someone's mic is open. So it needs to go down like that. So the derivative is decreasing in the I. In the someone's mic is open. I'm not sure who is it. I don't want to be looking for it. Just close it. But anyhow, yeah. So this is the ith axis, and along the ith axis, your gradient, your partial xi, needs to be going in the negative question. Okay. Do I have to look for it? I'll look for you. Whose mic is open? God damn it. Some guy forgot. Oh, it's Daniel. No, it's not Daniel. Okay, I don't know who it is. Doesn't matter. All right. Anyhow, let's come back to our example. So, so it's the same one, right? I'll do it again. It was one. It was x1, x2 plus 1, x1 plus 3x2 plus 1, right? Right? Yeah. And now, but now you're asking it to be negative. Okay. Okay. So this is the, again, let me remind you, this is partial 1g, partial 2g. And here we're asking for partial 1g to be negative. Right? But x2 is in the unit cube. So this is only possible when they're both the minimizers of the form 1, 0. Okay, here it could be 0, whatever. But here it has to be 1, 0. Do you understand?
I have a question.
Yes.
if x1 is equal to 1, shouldn't x2 be lesser than equal to -2? Why is it 0?
Why is it 0? You mean over here?
Yeah, because you said x1 is 1, so then 1
Oh,
times 1 is
yeah.
1.
Okay, what happened? You're right. Okay, so it's never possible. Yes, thank you so much. Yes. So this would be 1, 1. So you get x2 is less than -2. Thank you. Oh, thank you. Which is never possible. I will fix that. Yes. Okay, thank you. Yes. All right, that's great. That's good job. That's great. Yes. So you get the minimizer is not allowed to be on the upper bound. Perfect. Okay, thank you. Thank you so much. Okay, any questions about this? Okay. And then when you're inside, you are exactly equal. And so you just have this thing that I compute over here. So this would be an inverse over here. And what was the value? It was 1, 0. All right. So this is the, if you're inside, which is not, what? Oh, yeah, it is. Oh, yes, thank you. Yeah, I don't know why I do this, so I forget. But anyway, so you can see a problem, right? It says that in fact your minimizer can only be in the at the boundary. Yeah. All right. Anyhow. Okay. But this is actually in the boundary. In boundary. So yeah. Anyways. Okay. What else? Yeah. So now this is it showed up in your homework, and so let's try to understand this. So here's a C1 function, and suppose your domain is the simplex. I hope I have a picture here. Yes. So this is the domain is just this plane. Okay. So this is the plane. It's not a polytope. It's just the plane. It's like that. If it was less or equal, it would be the entire pyramid. Okay. So less or equal than R is the pyramid at the origin. Okay. Like, I don't know how to draw this. Let me try. It will be like this. All right. That's mastery right there. Yes. Anyways. All right, good. Yeah, why is omega closed? And why is it only its boundary? So can anybody tell me why is it only its boundary? Do you remember anything from or anything from second year calculus? All right, anyhow. The reason is if you put any ball on the polytope, it intersects both the set and the complement. No three-dimensional ball is fully contained in the simplex. Okay, so here's a proof in case someone asks you in a job interview, is equal to omega, because any ball, any 3D ball uh, uh, is never fully contained in omega. Okay, because this is the 2D surface and a ball is 3D. You cannot live in the 2D plane. You're a 3D human. So that's basically the idea. Good. Questions? Yeah, it contains its boundary, but what I'm saying is it is its boundary. There's no interior. So interior of omega is empty. Is that okay, Daniel? Yeah, good. when do we have that x is in whatever? Visible directions. Do I want to ask you about this? We'll just do it. All right. So let's find the visible directions together. So you start with the minimizer on the plane, and you want to find the v, the directions that keep you in the plane. Okay. Just heuristically, suppose it was just the. What's an easy example? Can you tell me one? Okay, here, XY plane. All right. Suppose your guy is like. No, let's do it like in the simplex. Okay, so you see this is the simplex, right? Let me do it in a different color. Like, come on. See, like this is the simplex, like a little dump. I don't know. What V will keep you in the plane? Can you guess? Suppose X star is like over there. How can you stay in it? Where shall it point? So you cannot move like this. You cannot move like this. You can only move along the slope of the plane. All right, very good. Now let's do mathematics. So summation of vi plus xi needs to be in the simplex. So it needs to equal r. So that means the sum needs to equal 0 for the feasible direction. Okay, these are the feasible vectors. Okay, all the guys that satisfy this. Okay. All right, and to have local min, when you take dot product, you need it to be non-negative, right? Local max, you need to be non-positive. Like this is gradient at x star dotted with v, right? What? I can put parentheses if it helps. All right, good. I'm going to ask you some questions. This is boring. So, oh, I see. No, I have to prove the theorem. Right. So, suppose one of the x's is strictly positive. This condition with the gradient is very complicated, even for you guys to just do it by hand in a quiz or test. So, we will derive an easier condition to this one. So, here's how you do it. Right, yeah, I remember now. So I thought I fixed this. So this is a minus over here, and this is a plus. Okay, it's a small typo. People told me in Piazza, I forgot to fix it on the OneNote. I fixed it on Quarkus. All right, so here's what you do. You set this, and then VM equal to 0. Okay, so I should do the work of how you get this. So and this will be xj, xi. Okay, so let me justify this from here. So all the VMs that are not ij are 0. So you're left with df dxi vi plus df dxj vj bigger or equal than 0. Okay. Then you plug in the xi over here. So you get minus partial of xi with times xi, and then a partial of xj times xi. Okay. Let me, anyway, so then you factor it out. So then you have exactly this. Now let me ask you this: why v equal to 0, 0, 0, 0 minus xi 0, 0, 0 xi 0, 0, 0 is feasible? Can someone tell me? Why is this vector feasible? Yes, very good. Because summation of vi is equal to minus xi or vk, whatever, which is 0. Okay, so we are allowed to do this, and we do this, and you get this. Okay, so hopefully I have one more slide here. Yes, good. So again, this is xj, xi. Now, because xi is strictly positive, it forces this product to be a non-negative. Okay, so the middle step here was just partial j of f minus partial I of f is non-negative. Okay, do you understand? Is that okay? All right, good. So in other words, that you will see later, you have that, okay, I'll write it here. If xi is positive, then the minimum from j1 to n of the partial derivatives is equal to partial of I of f. Do you understand? So it says that if one of the directions is positive, the feasible, like for your minimizer, then you attain the minimum at that partial derivative. Okay? I mean, this is also explained in the other textbook, because you have a homework question with a simplex, right? So you can read more details there, or you can ask me if you want. So, but here's the main result that he doesn't state it, but I thought I should. So, here, come on. So if x is a local min, we just proved that for all j not equal to I, you have this inequality, okay? So in other words, this guy is equal to the min of the partial m's of this guy, okay? Good. But now if you are convex, it works both ways. All right, so in other words, this is true if and only if this is a local min. When f is convex. Okay, so you can go both ways, and that's very nice because it tells you that if you want to prove that a point is a local min, just compute all the partials and compare them. I mean, you'll see it in the homework question. Some people already did this, you know. So, okay, let's do an example. Let's come back to this. Same thing, but now look at it in the simplex. Death. Can't believe it, man. Like, it's like I have amnesia or something. Like, unbelievable. This is pain. Oh my God. Ah, this is gonna be a nightmare. Can't believe it. All right, let's. You know what? I'll, you know, because I'll do it by hand. So I just, well, anyways, okay, so we found this from last time. And again, I'm sorry, I will retype this. It's the same matrix. We did this. Okay, so it's 113. I will fix it. I'm very annoyed. And let's check what happens from our theorem. So our theorem says that if one of the xi's is positive, then this is what happens for your partials. So let's open this up. So it says that you have this formula over here. So now I'll do it again by hand. So again, we computed this. It was x1, x2 plus 1, x1, 3x2 plus 1. Okay. Partial 1g, partial 2g. Now, suppose that x1 is strictly positive. Can someone tell me what will be the inequality? Okay. So you put these two and you get that x2 will be a non-negative, which is always true. So there's no new information here. Like your minimum could be at the, you could have one of your components be positive. Yes. But now suppose, is it next slide? Suppose now that x2 is positive. Now you get a problem. Okay. You get x1 plus x2 plus 1 needs to be bigger or equal than x1 plus 3x2 plus 1, right? Is that okay? Because now you flip the derivatives. This is the partial 1g, and you're asking it to be bigger than partial 2g. Right? Is that okay? Okay. So what is the implication from here? What do you think? No, what is it? Tell me, yes. Yeah, and which implies what? No, it does, yeah. Oh, wait. No, it doesn't work. Yeah. Yeah, because you have this and this. So impossible. Yeah, thank you. Yes. Yeah. So okay, but there's an implication. So the minimizer will be of what form? What will be the form of the minimizer? What will be the second component? So what's the second component? You're almost there. So what is it? Yeah, right? Because if it's strictly positive, you get a contradiction. So x2 is 0. And then x1 can be anything. It will be actually, it has to be strictly positive. Yeah. I mean, could it be 0? It might be 0. Yeah. Actually, if it is 0, you get a contradiction, right? You get 1, 1. Why? Oh, yes, from this summation. Very good. Good thing. Someone is paying attention because I'm not. Yes, very good. So then that gives you that x star. It gives you that x star 1 plus x star 2 is 1. which implies that x star 1 is 1. So the minimizer is just 1, 0. Very good. Good job. We don't have, and this is what we found, remember? Do I have to go to that slide? Okay, I'll go to that slide. Yeah, here. Isn't that cool? You could take an inverse, or you could do the crazy stuff we did. Just take the inverse. I guess that's the lesson. But I don't know, the methods agree. You got the same minimizer in a way, because it's almost the same problem. This is box constraints, but one is containing the other. They intersect. Okay, whatever. Questions from Zoom? Daniel says it's the homework and X2 is a contradiction. Yes. Perfect. Man, I wish Daniel had a mic. So annoying. All right. Good. So our convex stuff will come back. But now, so what we just did, we talked about constraints, right? Simplex and the box constraints. But you came to this course for general theory, so that because you never know what you're going to see. So now let's talk about compact constraints. Okay, so omega will be some compact set, and we will prove minimization results. All right. So compact was closed and bounded. First, I have to justify that you will always have a minimizer. And so we will prove this theorem from second year. That if your guy is continuous and compact, then the minimizer exists always. Okay. And it's not unique. So for example, you know, we've seen these pictures, right? Like a sin X kind of guy, and then you cut it, right? -1, 1. So you can have many minimizers, but you need it to be compact because it could go down to like -infinity. So you're not allowed to have infinite domains because you could have your guy going down. All right, good. And also you need continuity because, for example, -1 over x in open 0, 1 goes to -infinity, right? So it goes like this. Right? So that's why you need continuity. And that's why you need bounded. Right? Good. All right. So we talked about this a bit, that the min might not exist, but you can have a lowest lower bound, a greatest lower bound. That's called the infimum. So for example, infimum of open 0, 1 is what? What's the infimum of, Yeah. And then, of course, if you put infinity, you get -infinity. Okay. So it does exist. It's just infinite. Question? Okay. Okay, good. So that's why we're not allowed to use min yet, because we haven't proved its existence. Okay, so we have to use this notation called infimum. All right. So I don't know where but you've never seen this stuff. So let me give you another definition for infimum. that this might be the last time you see it, the first and last time, I don't know. But here's the definition. So a m real number is infimum for a set A if you can find yi in A such that they converge to M. So yi converges to M from the top. Okay, so the picture you should have in mind is you're on the real line. This is M, this is A, and then you have a bunch of points clustering to it. Okay. So let me do a stupid example. Take A to be open 0, 1. Can someone tell me a sequence of yn that go to 0? Yeah. Okay. 0 is not in A, but you can always find some sequence going to the infimum. That's the equivalent definition. So a point is called the infimum if you can find the sequence going to it from the top. That's all. Good. And they're all bigger than the infimum. So you need it to come from there. All right. All right. So whatever you're more comfortable with. So we apply it to our stuff, and let me explain how. So let me do it here. Yeah, so we're looking at this infimum. So let's do it carefully. What is this set? This is the infimum of the set f of x for x in K. Okay, that's what we're studying, right? All right. Yeah. And by this definition of infimum that we just talked about, it says that, call this guy M, there exists y, I call it, yeah, let me call it yi equal to f of xi. Is that okay? So that the yi's go to M. Is that a big jump? Shall I explain? Is that okay? Is that okay? Okay, I don't know, I can explain, you can tell me, I don't care, I don't care. You can just tell me. So again, this is a set from before, we called it A, and this is the infimum of A. And the definition of infimum is that you can find points, call them yi equal to f of xi, that go to M from the right. Okay, the xi is true because every y is of the form fx. So there is some pre-image because f is a function. Okay, that's how you get the xi's. Right, because this is a set of the form f of x. Okay, good. Like, I don't know, think about like this being e of xi. Oh, doesn't matter. Okay, good. Zoom. Right. Now, we talked about a definition of compactness that some of you said you've never seen this before. It says that if a set is called compact, if for every sequence, you can find a convergent subsequence. So if you remember, I talked about -1n. This is a DNE, but -1n for n even is equal to 1. So it converges. It converges for subsequence x to n. It goes to 1. Do you understand? So this guy does not converge, but it has a subsequence that does. That's the definition of compactness. That you can always find a convergent subsequence. Even though the guy might not converge, it has some subindex that does. Like even numbers, odd numbers, that's usually what we do. Okay, good. So that means, what's the next slide? Yeah, so you give me, here's the crazy set. Suppose it oscillates. It says that you can pick one of them that goes to x naught. And suppose this goes to some other point. But we're just looking at the guy who converges. Okay. Is that okay? I mean, this is theory that you've seen it, but like other people have not seen it, and you don't need to know the proof. Okay, this is the extreme value theorem. Like you didn't prove this in second year because you need all this machinery, right? That's the reason. Okay, good. All right, but f is continuous. So another definition of continuity that you might see, and it's more convenient, is that xn goes to x naught, implies that f of xn goes to f of x naught. That's the definition of continuity, basically. I mean, it's called sequential continuity. Yeah, but it's the same thing in Euclidean. Whatever. Okay, so this has a limit, and can someone tell me how do I finish from here? Oh no, wait. Let me. You have 337. You have like. I will come back to you at the end. Anybody else? You mean? What do you think? Do you know about return to proof? Huh? Yeah, we're trying to prove that f of x naught is equal to m. So you obtain the infimum. So you understand? So can you prove me this? Huh? Oh, no, just from this limit stuff that we just wrote. It's like just combine. You don't have to do epsilon delta. Just tell me, like, put this and this together, you get the result. What should I put together? Do you know? Yeah. Right. Right. I mean, it goes to m, but and then what do you want? So again, I think let's do it together. So what are you saying? You're saying compare this guy with this guy, and then what do you want me to do next? Let me go on the slide. Which two results, which bullet points should I combine? Let me ask you that. Do you need glasses? Better glasses? Or yeah, okay, no problem. Yes. So we have f of x naught minus m, and then you will see this sometimes if you take more math. You subtract and you add the thing you want. Okay. Okay. Then you do a trick called triangle inequality. All right. So you have f of x naught minus this sequence. plus this sequence minus m, and you take limits. You don't have to do epsilon delta, just to take limits. So take limits and you get 0 plus 0. So you got that f of x naught is m. Is that okay? Good. I mean, this is the extreme value theorem. Like, there's no way you won't use this if you do any like data analysis. I mean, you will have compact sets, you will have minimizers. Like, how do you know they exist? That's why. That's the theorem. Tells you that they exist. Like, our whole course depends on this. Like, yeah, okay. Yeah, that was it. So, yeah, so f of xi goes to m, and so you combine the two limits, and you get the, yeah, the subsequence. There's more. Yeah, okay, yeah, and then you combine the two. So look at previous slide. All right, let's apply this for fun. Here's some functions that will show up as constraints. So that you're gonna say this all the time now. This from now on, I will try to have most homework questions to be of this form, so you get like good practice. So you're gonna have non-linear constraints, inequalities, equalities. And can someone tell me why this is a closed set? Can you guess very quickly? You should. I don't know why I'm keeping. Okay, but yes, it's because you have. I remember this as a because you have equalities. Whenever you have equalities, you get closed sets. Okay. So whenever you see less or equal, you lose that. You have open sets. But the moment you have this, you get closed because you can reach gx equals 0, the boundary. So it contains its own boundary. That's the definition of being closed. So the bound, no, can someone tell? I'll write it. The boundary is this together with this being 0. Okay, that's all. There's nothing. All right, let me finish here. Yeah, so anyhow. Right, and then, okay, so this is each of them is continuous, and if it happens that your set is compact, so anyways, we'll talk about this more next time. So if this is also bounded, like a simplex, then minimization of f over k exists, is equal to f of x naught. Okay, so I'm just coming back to optimization. So this would be your optimization set. You will have to prove in the homework that this is compact. So usually you just have to show it's bounded. The closed will be very easy. Okay, and then you will say from extreme value theorem, I know that there exists a minimizer. Okay, all right. So thank you. Yes. Oh.
Hi, Prof.
Oh, hi.
So you know how you said taking the limit is easier than showing the partial derivative? Can you give an example? Like a simple
The
example?
one I just did, right, with the quadratic form, that was an example. Like, remember last time I spent like almost 10 minutes trying to compute that partial derivative, and it was a mess. So that example we did today, like with the quadratic form. Can you see? Yeah. Let's see. Are you there?
Yeah.
What's another example? I mean, I think we can also. Let's see. I don't know. Like, suppose you have something like crazier, like this one, right?
Mm-hmm.
How would you? Imagine if you sit down and start taking partial derivatives. This would be a nightmare, right?
Yeah.
But if we do it with directional, you can use a chain rule. So let me see. So how do we? So this is limit h goes to 0. And then you have x plus h. Like this. Okay, let's see. Does this help you? So yeah, let's look at it. So remember, this was, oh yeah, remember we could factor this out. So you have x, t, I, x, and then you have, remember it was like some h guy, a transpose x, I think. And it was like, so it was like v, right? This is v. And I don't remember all the terms. What was it? It was like h, what? A, what was it? Maybe like VAX or XAV, and then remember? Hello?
HX transpose AV.
Right, okay, but from here, yeah, so then from here we can do the same thing. You have minus H, some A transpose X thing, and yeah, some, I don't remember now. It was like this, and you still have an H left, minus 1, and then you use regular calculus, right? So from here, you just say that this is over H, and you use regular calculus. So this is of the form minus H gx minus 1 over H, and it goes to whatever that is in first year calculus. What is it? Is it minus 1? It's minus 1, right? Minus 1 with this gx, right? Hello?
How is it -1?
Yeah, no, it's like that. What's the derivative of lambda? Like, you know, like e to the minus x with a constant g is equal to minus e minus x g times that g guy. So this is the first factor, and then you pick out this constant. Is that okay? So if you, is that okay so far? Hello?
Sorry, can you repeat that one more time?
Like which step?
From like when you get to e to the power of negative h gx.
Yeah. This is like a first year calculus, right? It's of the form minus h times some constant minus 1 over h.
Mhm.
And if you take the limit of this, you get minus c. Yeah, I mean, you can do this. It's L'Hopital's rule.
Oh, okay. Yeah.
Yeah, yeah. Right? You
Yeah.
take derivative of both sides, right?
Mhm.
Okay, good. Is that okay?
Yeah. And you know how you went from the first step to the second step to the power where negative x plus h transpose a x plus h. How did you get the second part? Like the long,
You mean this guy over here?
yeah.
Yeah, this is the same as, I mean, I don't know if this is correct, but this is what we did in that example with the quadratic form. Remember? Like you can see it from there. Oh, this one is easier than that. What am I talking about? This one, I just opened it up, right? I have x hv, and then x plus hv, and then I just used linearity. And I got 4 terms, right? Hello?
Hello. Yeah. Can you show how you did that? Because it's kind of confusing.
Yeah, like, no, let's do it together. So you see this over here?
Yeah.
Can you tell me what is the first term? Hello?
Yeah. I'm not sure.
No, you have to try. I mean, this is like so this is a vector, another vector. This is a matrix. And
Yeah.
then you have, so what will be the first term when you cross multiply everything?
X1 plus HB1 times A.
Like that?
Yeah. Like,
Times
isn't
what?
it times X plus HV?
No, but this is what we had over here. I'm saying like to cross multiply.
So is it AX plus HVA?
Like, so let me give you the first one. The first one will be this, right?
Okay.
What will be the second one?
XTAHV?
X what? Oh yeah,
X
XT.
transpose
Yeah.
AHV?
What about the third one?
HV transpose AX?
Yep. And the final one?
HV transpose AHV?
Yeah. You see, that's how we got. I mean, I don't know. I probably made mistakes here. It's probably like VV. Yeah. Okay.
Okay.
So yeah, like this example, like if you sit down and do partials, you will kill yourself because it's like so many terms.
Mm-hmm.
But here we just use linearity, and then I use first year L'Hopital.
Okay.
Anything else?
No, that's all.
What's the number? So this is from last week, right? Because I posted, I see. 20, I have to guess. So you said, what was the result? Oh, it's simplex or bound? Simplex. Okay. Yeah, I just want to find the whole. Yeah. So this is in the textbook, right? Can you open? You've seen it in the in the checkers if you go to the textbook, and you go to the where the homework was for the simplex, like 211 something. So yeah, it's the example, right? You found it? So where is that? What's the page? Yeah. Right. Doesn't he apply? Yeah, he applies it right after, right? But anyways, I mean, no, I even did this in class. What do you mean? Oh, no, 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 no. Remember, we said that, this guy is so bounded. He's the opposite of bounded. No, there is no question. No, the condition will always be this one. There is no condition. Oh, by the way, no, I think, no, even for physical dimension, there is no law. Yeah, yeah, so the physical dimensions are complicated, but you know what to do. You just have to complete the function. To check that something like the one you need. So, you do it all time and. Yeah, so. Right, so it means from the home. So you have to check whether, so, uh, you have to check first of all, can all be decided from zero? Is that a minimum or a maximum? So if or whatever. No, then, okay, yes, yes. Then, suppose that almost, suppose it's not known, is only the thing where the no, otherwise you get a. Then what is the for the function? So the first step is the first suppose there is one positive, then the mean minus will be the function of the function, right? But make the function of the function, you have to balance. Yes. Two possible, x minus 3. Suppose x 1, after the 1, this is part of the 2. Yeah? Now go for x2. After the 2, this is part of 1. Now put the 2 together. Yeah. So all then the other one is the from. I mean, if x 1 0, go down and find one problem of the minimum. Fine. You find one problem, the x 1. Then I have to find the rest. You don't have to worry about x 1 anymore. So you select one of zero. So then you have projects, 3 years, 4. You understand? You told me if, so you told me if x, y, 0, what do I do? Yeah, yeah, x1, the first component is the minimum is done. For this component, now we have to find the reference. Yeah. The minimum. Yeah, okay, good. I mean, that's the thing. If I can do what I find, No, I'll come. Just sit there. No, do it yourself. It's a homework.